In this tutorial, we will be discussing enthalpies of reactions. When a reaction is multiplied by a factor, delta H is then also multiplied by that factor. This is because delta H is an extensive property, meaning that it depends on the amount. So for instance, if we take carbon and oxygen and combine it to make carbon dioxide, it gives off 393 kilojoules. However, if we then multiply that by 2 and have twice as much carbon, we have to multiply that by 2 as well. If the reaction is reversed, then the sign of delta H is reversed. Notice it's negative here. Once we reverse that sign, that chemical equation, carbon dioxide is breaking down to carbon and oxygen. It becomes a positive. Furthermore, if a reaction can be expressed in a series of steps, for instance, this right here, if we're trying to get from here to here, and it takes 2 steps to get there, the sum of the reaction is the overall reaction is the sum of the steps. Let's do an example. Calculate the delta H for this reaction. This is the overall reaction that we're trying to get to, and these are the steps that the chemicals go through to get there. What we have to do is match up these to make it look like that one. Alright, so take it step by step. We have copper on the left. We have 2 different coppers, and so we are going to move on and go to the next one. Copper CuCl2, copper 2 chloride. It's on the left. If I look at all these reactants and all these products, I find copper chloride right here. It's on the right hand side, but we need it on the left, so we're going to flip it around. CuCl2 solid yields Cl2 gas and Cu copper, Cu solid. Because we flipped the equation, we're also going to flip the sign, 206 kilojoules. It was originally negative. I now have it as a positive. Okay, so we have that one taken care of. Let's look at copper 1 chloride. Look at all of our chemicals and look for copper 1 chloride. It's right here, and it's on the right, and so is this one. So we don't have to flip this one. 2 copper solids plus chlorine gas yields 2 copper 1 chloride solids. Because I didn't do anything to it that time, I'm going to leave it as a negative 36. Alright, so now we want to try to add these together to make it look like this. I said before that we had copper in 2 different places. We have 2 coppers here and 1 here. We can cancel those out, just like you were doing math questions back when you were in 4th grade, where you added things down, added 2 equations, like in algebra. The chlorines can cancel out, and we now have copper solid plus copper 2 chloride solid is yielding 2 copper 1 chlorides. We're going to add these numbers up to get our final delta H. The delta H of the reaction is 170 kilojoules. That was a fairly easy one. Let's take it one step further and do a harder one. Alright, so we have NO2 here. We have NO2 here. Is that the only place you find NO2? And it looks like a yes. So we want to keep that as is. So this is on the left, this is on the right, so we're going to flip it around. So 2 NO2 gas yields 2 NO plus O2. Because I flipped that around, I need to flip the sign. It's now positive 116 kilojoules. Alright, let's move on. H2O. Look for everything that has H2O in it, and you'll find it right here. It's on the left here, and it's on the left as well here. So 2N2 gas plus 5O2 gas plus 2H2O liquids yields 4HNO3 aqueous. Delta H, we didn't do anything to it, so it's negative 256 kilojoules. Alright, now it's going to get a little bit trickier. HNO3, we have 4 HNO3s on the right on this one, and that's the only place you find HNO3, so that's fine. Then NO, we have NO here, and we have NO here. So let's explore the reasons why we would have NO in two different locations. You'll notice that this also has an N2 involved. Well, there's no N2 in the final reaction, but there is an N2 here. So obviously those two are put together to cancel out. So since this is on the left, I'm going to need this one on the right. So I'm going to reverse this. 2NO gas yields N2 gas plus O2 gas. I reverse that, so that becomes a negative 183. Now let's take another look at it. We have 2 N2s here, only one here. So I'm going to have to multiply this entire equation on the bottom by 2. So now we have 4 NO gas, 2 N2 gas, and 2 O2 gas. Because I multiplied that by 2, I have to multiply the 183 by 2. That becomes negative 366 kilojoules. So I no longer need this equation, so I'm going to scribble it out as much as I can because I don't want it to confuse me. We want to make sure that we realize that it's not part of the final summation. Okay, so I can cancel this and this out now. Alright, so let's look at some other pieces of the puzzle. Alright, so the NO, we have 2 NOs here. We have 4 NOs here. However, we ultimately need NO on the right. Let's see if we can figure out a way to make those cancel out so I have more on the right than I do on the left. I also have 2 NO3s here. If I multiply this entire equation by 3, that brings us to 6 NO2s, 6 NOs, and 3 O2s. Because I multiplied that by 3, I need to multiply our top delta H by 3 as well, to be 348. That means this top one gets scribbled out because we don't need it anymore. Alright, let's see what we can cancel out now. The HNO3 is fine. The O2s, we have 5 on the left, and we have 1, 2, 3, 4, 5 on the right. Those can cancel out perfectly. The NOs, we have 4 here and 6 here. We can cancel that out, and that leaves us with 2 left over. Alright, I don't think we can cancel anything else out, so let's add them all up. 6 NO2 plus 2 H2O yields 2 NO. Let's put our physical signs here. Gas, liquid, gas, and 4 HNO3s. If we add all that up, it comes out to be delta H is equal to negative 274. But if you look at the chemical equation, 6224, these are all divisible by 2, which is good because it doesn't quite look like this one yet. Notice 3, 1, 2, 1. Alright, so let's divide everything by 2. 3NO2 plus H2O, gas, liquid, I keep forgetting my physical signs. Then 1 NO gas and 2 HNO3. When I did all that, I have to divide my total by 2 as well, to be negative 137 kilojoules. That was a really complicated one, so if you followed that, that's great. The standard state is the state of the material at a defined set of conditions. Pure gas is exactly 1 atmosphere pressure. Pure solid or liquid in its most stable form at exactly 1 atmosphere, and temperature of interest is usually 25 degrees Celsius. And a substance in a solution is with a concentration of 1 molar. The standard enthalpy change, delta H, we refer to this little circle here as a knot. So delta H naught is the enthalpy change when all reactants and products are in their standard states. The standard enthalpy of formation, delta H of formation, is the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. So what it's made of. The elements must be in their standard states. The delta H of formation for a pure element in its standard state is 0 by definition. Reactions of elements in their standard state to form 1 mole of a pure compound. If you are not sure what the standard state is, there's probably a chart in your book somewhere. Chances are it's an appendix, or it could be part of this chapter. Since the definition requires 1 mole of a compound to be made, the coefficients of the reactants may be fractions. So for instance, the formation of carbon monoxide is carbon and oxygen are the elements that make it up. However, we need everything in a 0 formation, delta H of 0. If you look up carbon, carbon has 2 states. It could be diamond, or it could be graphite. The one that's the delta H of formation of 0 is the graphite, and that's why it's used. Also, we have O2 as the gas, making carbon monoxide. Because we want this to balance out to be 1, the carbon sulfide, solid graphite, is reacting with 1/2 of an O2, because we want the formation to be 1. So let's take a look at this. Carbon plus oxygen, O2, is yielding CO2. Now if we look in our charts, we find that solid carbon in a graphite form is the 0. Oxygen is gas, and carbon dioxide is gas. So let's take this again. We're trying to make Al2S4 3. Let's look at our elements. We have aluminum, we have sulfur, and we have oxygen. Aluminum is a solid metal. We need 2 of them. Sulfur, there's 2 versions of sulfur. There is rhombic, and there's monoclinic. You'll find that the rhombic is the one that's 0. So we're going to use that. So in solid rhombic form. Now let's look at how many we need. There's 1 here times 3, so we need 3 of them. Then oxygen is supposed to be O2, and it's a gas. There's 12 divided by 2 is 6. Any reaction can be written as a sum of the formation reactions, or the reverse of the formation reactions, for the reactants and products. The delta H of a reaction is the sum of the delta H of formation for the component reactions. So the delta H of reaction is the products formation minus the sum of the reactants formation. In case you are unknown, this means sum, means adding it together, and N is the coefficient of the reaction. So in other words, when we're looking at the chemical reaction, the N is this. Alright, so chances are, once again, you'll find in your book either a chart in the chapter or an appendix in the back that gives you these formations. You would never have to memorize these. These pretty much are given to you. You have to look them up. If you don't have them in your book, you can typically look them up on the internet, and they're pretty readily known. So we want to do the products minus the reactants. Alright, so the products are CO2, negative 393.5. We only have one of them, plus we have two waters, which are negative 241.8, minus the reactants. So CH4 is, we have one of them, negative 74.6, and we have two oxygens, which are 0. That comes down to negative 393.5 minus 483.6 plus 74.6, which is equal to negative 802.5. Note the units, kilojoules per mole. That's all there is to it. Let's do another one. Alright, so we have our heat of formations here. Our products are 4 times carbon dioxide, which is negative 393.5, and 2 waters, which is negative 285.8. Notice the physical state. This is liquid. Negative 285 is liquid. This, however, was gas, and that number changed. So make sure you're checking the physical state when you're doing this. Minus the products, or the reactants, which are 2 times 227.4 and 5 times 0 for oxygen. That comes down to negative 571.6 minus 1574 minus 454.8, which is equal to a delta H of negative 2600.4 kilojoules per mole. This one's a little bit more difficult because they don't actually tell you what the chemical reaction is, so we have to figure that out. So octane is C8H18 plus O2. Chances are you don't know what octane is yet. Your teacher would probably have to tell you that. Yields CO2 and H2O. So octane is a liquid, oxygen is a gas, CO2 is a gas, and we're going to count H2O as a gas. Alright, so how many kilograms of octane must be combusted to supply 1.0 times 10 to the 11th kilojoules of energy? Before we do anything, we had to figure out how much energy is produced in this reaction itself. So, first thing we need to do is balance it out. Remember, we want this to end up being 1, so we can have fractions here. So 8 carbons, 9 waters, that brings us to 25 O2s. So it's going to be 25 over 2 O2s. Alright, so the products are 8 carbon dioxides, which is negative 393.5, and 9 waters, which are negative 241.8, minus the reactants, which is 1 of the C8H18, one of the octanes, and 25 over 2 oxygens, which is 0. That comes out to be negative 3,148 minus 2,176.2 plus 250.1 equaling negative 5,074.1 kilojoules per mole. Alright, so we're trying to figure out how to get this much energy, how many kilograms. So that's our starting point, 1.0 times 10 to the 11th kilojoules. We can use our delta H as a conversion factor. There are negative 5,074.1 kilojoules in every 1 mole of octane in this reaction. So in 1 mole of octane, there are 114.2 grams. This is the molar mass of octane. So there's 8 carbons, so 8 times 12.01, and 18 hydrogens, so 18 times 1.01 added together, and that's what you get. 1,000 grams, 1 kilogram, because it's asking for kilograms. So 1 times 10 to the 11th divided by 5,074.1 times 114.2 divided by 1,000. That comes out to be 2.25 times 10 to the 6 kilograms. Technically I had a negative in there, but because this is just how much it will supply, I'm going to automatically make that a positive. You can't have a negative mass anyways, so it would make sense to make it positive. 2.3 times 10 to the 6 kilograms of octane. I put it in 2 significant figures because I had 2 in the initial question. Okay, we're going to do one more and then we'll be all done. Calculate the delta H for decomposing of 10.0 grams of limestone, in which is calcium carbonate, under the standard conditions. So, products over reactants. Products minus reactants, pardon. We have 1 CO2, which is 1 negative 393.5, and 1 calcium oxide, which is 1 times negative 634.9, minus the reactants, which is calcium carbonate. We only have one of them, 1 times negative 1207.6. That comes out to be 179.2 kilojoules per mole. We have 10 grams of limestone being used. So 10.0 grams of calcium carbonate over 1. We need the molar mass of it to get to moles. So calcium carbonate, after looking at the periodic table, is 100.09 grams. 1 mole of calcium carbonate. So 1 calcium, 1 carbon, and 3 oxygens added together gives us 100.09. So when 1 mole of calcium carbonate decomposes, it gives off 179.2 kilojoules. Alright, so 10 divided by 100.09 times 179.2 is 17.9 kilojoules. And that's how you incorporate enthalpy into chemical reactions.